Hi, I'm Cornel, and together with my colleagues I've been working on a method for watertight incremental Heightfield tessellation. Heightfield tessellation is the process of creating a triangular surface that approximates a given height field. This is a well-researched topic, especially its application for terrain rendering, but the efficient tessellation of dynamic height fields, like the output of a flood simulation, remains very challenging. Since the simulation data are generated on the fly, tessellation also has to happen on the fly, so we cannot rely on pre-computed acceleration data structures as used in terrain rendering systems like Rome, raster, or geometry clip maps. The goal of tessellation is that all created triangles have roughly the same size and screen space, like in this example. On the left, we visualize the triangles of the terrain height field in green and the water height field in blue, where a change in color indicates a change in triangle size. As you can see in this zoom animation, the triangle sizes are adapted continuously to achieve the desired screen space size. This task is typically performed with the help of the hardware tessellation unit in modern GPUs, which is very efficient at subdividing triangles. However, when I show you two consecutive frames of this zoom animation, you will notice that almost none of the triangles change their level of detail from one frame to the next. Only a handful of triangles have to be changed, the rest could be reused from the last frame. But this also includes reverting a subdivision when triangles are too small already. And this is something that hardware tessellation cannot do. It can only subdivide triangles but not merge them together again, which is why you have to create the entire triangulation from scratch every frame. Instead, we want to cache the entire triangulation and only incrementally update it where needed, which is significantly faster than hardware tessellation. So how do we do this? We start with a height field defined on a rectangular area and create a very coarse and initial triangulation that covers the entire area. This triangulation is made up of 4 different types of right triangles, illustrated here by different colors. We now define subdivision rules to split these triangles into smaller versions of themselves. A popular splitting scheme is the longest edge bisection, which splits a right triangle along the bisector of its hypotenuse. With this scheme, we can split an original triangle into 2 smaller ones of types we haven't seen before. So for these 4 types, we also need to define subdivision rules. Luckily, the longest edge bisection splits each of these triangles into a pair of triangles of the first 4 types, which means we can apply these rules recursively. That sounds very easy, so let's see how well it works. In this example, we have only 2 triangles that we can split. And we split them into 4 smaller ones, and now we can split, for example, the blue triangle on the left again, and then, for example, the purple one on the bottom left. But now we run into a problem because we have created a T-junction, meaning we have split one triangle without also splitting the neighboring triangle along its hypotenuse. Let's look at this in 3D. The split introduces a new vertex on the shared edge, which is then sampled on the height field and shifted along the height dimension. Now the triangulation has a hole and is no longer watertight. This reveals the background of the scene, which is noticeable as pixel flickering in a visualization. To guarantee watertightness, we need to improve our subdivision rules. If we want to subdivide this blue triangle, we cannot just subdivide this triangle independent of its neighbors. This is why for each cached triangle we store explicit triangle adjacency information. This information allows us to find the neighboring triangle that shares the hypotenuse of the triangle we want to subdivide. Only if the shared edge is the hypotenuse of both triangles, we split both of them simultaneously. If we want to split this triangle afterwards, we can look for the neighbor along the hypotenuse with the triangle adjacency information, and we'll find out that the shared edge is not the neighboring triangle's hypotenuse. So no subdivision can happen here unless the triangle on the left is subdivided first. From this neighbor check, we can formulate another subdivision rule. Given our 8 triangle types and all the arrangements they can have, there are only these 4 valid combinations where the shared edge is the hypotenuse of both triangles. So for subdivision, we only have to find and replace these valid combinations with 4 smaller triangles. The other way around, for merging, we remove the 4 small triangles and reinstate their 2 parents. This guarantees that T-junctions can never happen during subdivision. The challenge that remains is how to apply these rules concurrently. If we want to split these colored triangles in a GPU implementation, we want to perform the subdivisions concurrently for maximum efficiency, so we perform each subdivision in its own thread. In both threads, we split the triangles and then update the adjacency information of the neighboring triangles to refer to the newly created ones. And you already see what will happen. In each thread, there is a reference to an adjacent triangle that no longer exists, because it has been subdivided in the other thread. Without synchronization, it is not possible to guarantee that the triangle references in the cached adjacency information remain valid. Low-level synchronization of the read and write accesses to this information are possible, but that is a complex task. Instead, we propose a higher level synchronization with the help of our triangle colors, and we adopt the concept of task scheduling by graph coloring. In terms of graph coloring, any recursive application of our subdivision rules results in a valid 8 coloring of the plane. If you look at this colorful triangulation, you can see that no triangles of the same color share an edge. This means that all triangles of the same color can be processed concurrently without any issues. Only between the different colors synchronization is necessary. And even though we have 8 different triangle colors, we only have 4 valid combinations of colors. So we only need 4 separate processing passes for subdivision and merging with explicit synchronization in between. Let's put it all together. We start with a coarse initial triangulation that covers the entire height field. After that, or whenever the height field data change, we resample the cached vertices at the height field. After that, or whenever the camera changes, we evaluate the level of detail of each triangle and decide whether to keep it, subdivide, or merge it. With this information, we loop over all cached triangles in 4 separate passes for the 4 triangle colors with synchronization between them, and apply 1 level of subdivision to all necessary triangles. We then loop over the triangles again in 4 separate passes and merge triangles as needed. We now have a complete triangulation that we could render, but we only performed 1 iteration of subdivision and merging, so locally the desired level of detail might not be reached yet. If further changes are needed, we repeat the process and loop over these steps again until no further changes are required. If we reach that point, or if a termination criterion is reached, such as processing time budget is used up, we render the cached triangles. This is the general workflow of our technique, but in the paper we also describe additional important performance optimizations. We compare the performance of our work to previous work, including a hardware tessellation approach shown in orange and 2 cached tessellation approaches in blue and green that do not produce watertight triangulations. Our method, shown in red, has a very stable runtime performance that outperforms the other methods, especially when using higher order interpolation during vertex sampling. Additionally, the triangulations of our method exhibit the smallest error in approximating the height field surface. It is therefore faster and more accurate than the current state of the art, while at the same time guaranteeing a watertight triangulation without visual artifacts. Finally, I want to highlight that the animation you see here is taken from our reference implementation, for which you can find the source code in the supplemental material of our paper.